Hey everyone, and welcome to this explainer. Today, we're skipping the dry textbook definitions and going straight for the good stuff, the ultimate master builder's blueprint. If you've ever wondered how elite software engineers take raw logic and construct the digital infrastructure that basically runs our world, well, you are in exactly the right place. We're going deep into data structures and algorithm analysis.
Think about it. How do you actually maximize results when you're staring down a complex, real-time issue? This isn't just a fun thought experiment. It's the core driving force behind our entire source material today. The goal here is to get you so comfortable with data structures and algorithms that you can walk up to a whiteboard, look at a massively complex problem, and actually solve it while keeping things crazy efficient. We're turning pure theory into absolute real-world power.
So here is our game plan. We'll start with the ultimate computation toolkit, figure out how to organize the digital world, decode algorithm analysis, and then wrap it all up by solving some real-world problems. Let's get right into it.
Part 1. The Ultimate Computation Toolkit. These are our raw materials.
You wouldn't build a house without knowing the difference between wood and steel, right? In our digital world, our materials start with the raw concept of computation itself. On top of that, we layer in algorithms, the step-by-step instructions. Then we bring in elementary data types, scale those up into abstract data types, and finally, form complete functional data structures. That's the fundamental hierarchy of literally everything we're about to discuss.
But where does all this magic actually happen? Enter the RAM model of computation. Picture it as your theoretical workshop where all these concepts come to life. By grasping this foundational model, we get a crystal clear look at exactly how a computer manages data and processes those algorithms. It is the absolute baseline environment we need to understand before we can even think about organizing things.
Moving on to Part 2, organizing the digital world and categorizing all this data.
Okay, so we've got our materials, but we need to organize them. First up, we split the world into two main camps. On one side, you have primitive data types. Think of these as your basic, indestructible Lego bricks. On the other side, we have non-primitive data types. These are the complex structures you build by snapping those primitive types together. It's basically the difference between holding a single brick and staring at an entire prefabricated wall. Once we've got those bigger, non-primitive pieces, how do we link them up? That brings us to our next major split, linear versus nonlinear data structures. A linear structure is exactly what it sounds like, a sequential arrangement. Imagine a line of people at a checkout counter. One item follows the next in a predictable, straight path. A nonlinear data structure, though, that's hierarchical or interconnected. It's a lot more like a family tree or a crazy map of cities connected by highways. Figuring out which arrangement to use is a huge chunk of the design process.
And here's the cool part. Once you nail these foundational linear and nonlinear structures, it's like unlocking a new level. You get the vocabulary needed to tackle highly advanced, intricate structures used in modern software. The source actually flags these advanced structures as critical self-learning topics. Because honestly, the basics are just the doorway. The learning never really stops.
All right, Part 3. Let's decode algorithm analysis. I like to call this the physics of code.
Writing an algorithm is one thing, but how do we know if it's actually any good? We've got a three-step process to figure that out. Step 1 is pseudocode, getting the logic out of your head and onto paper without getting bogged down by strict syntax. Step 2 is performance analysis, where we really start interrogating that logic. And Step 3 is measuring its footprint, specifically looking at space complexity, how much memory is this thing eating up, and time complexity, how long is it going to take to run?
Now, to really push our code to the limit and measure that complexity, we need specific tools. Enter asymptotic notation. You'll see this highlighted in the curriculum as both a core topic and a major self-learning requirement. These are mathematical tools used to describe the limiting behavior and performance of our algorithms. It's basically the ultimate stress test. It tells us exactly how our code is going to behave when the amount of data we throw at it grows toward infinity.
Our specific toolkit here includes 4 heavy hitters. We've got big O notation, which looks at your absolute worst-case scenario, omega notation for the best-case scenario, theta notation gives us the exact growth rate, and little o notation provides an upper bound that isn't tight. Grasping these 4 metrics is what allows a developer to confidently predict how a system will behave as it scales up.
But wait, the analysis doesn't stop there. A true master builder also dips into probabilistic analysis and recurrences to dissect really complex logic. You'll also run into disjoint set operations along with union and find algorithms. These are incredibly powerful tools designed to group elements and efficiently track what belongs together across massive datasets.
Theory is great and all, but we need to see it in action, right?
The source grounds all these theoretical concepts with a very concrete application, the analysis of a binary search. By taking a super efficient, well-known algorithm, like binary search, running it through our performance analysis and defining it with asymptotic notation, we get to see exactly why it's such a massive powerhouse in our digital toolkit.
Which brings us to our final section, Part 4, solving real-world problems and becoming the master builder.
Let's tie this all back to what you'll actually be doing. Take Learning Outcome 1.1, for example, applying queuing theory. This is literally how you model computer-based systems like managing a massive digital checkout line on a global e-commerce site. Then, with Learning Outcome 1.2, you take those asymptotic notations we were just talking about and use them to definitively analyze the computational performance of any problem you face.
Then, looking at Outcomes 1.3 and 1.4, it's all about playing matchmaker. You are learning to look at a nasty computational bottleneck and identify the exact appropriate data structure to fix it. More than that, you'll be able to identify the specific processes, modules, and algorithms needed, choosing the precise parameters for the job. It's all about knowing exactly which tool to pull from your belt for a very specific problem.
But honestly, a master doesn't just grab the first tool that works. Learning Outcome 1.6 hits the nail on the head. You have to be able to explore design alternatives. You need to look under the hood at their mechanisms, and most importantly, discuss their limitations. True mastery isn't just knowing how something works, it's understanding exactly where, when, and why it might completely break down so you can build redundancies against it.
And all of this culminates in Learning Outcome 1.5. This is the big one. This is where you take total control. You'll be able to design precise problem statements from scratch and confidently discuss the exact required data structures needed to implement a solution. You literally go from just reading the blueprint to being the architect who draws it.
So, that is the journey. We've gone from the raw materials of computation to the intense physics of asymptotic analysis, all the way to solving complex real-world problems. You have the data structures. You have the algorithms. The digital toolkit is open and ready in front of you. So the only question left is, what problem are you going to design next? Thank you so much for joining me on this explainer, and I really hope you feel ready to go build something incredible.